Good evening, my name is Sophie Krajmalnik, and I'll be presenting my data visualization project over visualizing International Science and Engineering Fair trends from the years 2014 to 2024. This includes over 14,000 projects analyzed from abstract data from the Society for Sciences Abstract Search. Science fairs are a crucial educational milestone for American students from elementary school to high school. The International Science and Engineering Fair, or ISEF, is a pinnacle of this experience as the largest international pre-college science competition. ISEF sees thousands of projects annually and gives out even more in award money, opportunity, and prestige. The abstracts the students produce provide various information about their demographics, category, competition, and findings, and are collected by ISEF, as well as their award results. There is limited data and research available about the environment of science fair, a clear gap compared to the depth and breadth of resources invested into science fairs. The existing literature focuses almost exclusively on the student experience for those involved in science fair, such as their motivations, attitudes, learning outcomes, and equity of access. What is absent from the literature is a qualitative analysis of the content of student research, student topics of interest over time, and whether this information correlates with success. Therefore, I will be investigating three core hypotheses. First, that AI, machine learning, and computing topics have grown significantly as a share of ISEF submissions from 2014 to 2024. Second, that certain ISEF categories receive systematically larger award dollar amounts regardless of how often they win. And third, that projects and categories that have grown in popularity over time win awards at a higher rate. Essentially, that judges are rewarding timely science. As previously mentioned, the dataset used is a Kaggle dataset that contains project entries from 2014 to 2024 with the requisite information. The dataset was then cleaned and some derived categories were applied in order to produce the final result, which had the title, category, year, abstract, country, state, awards, as well as a text category, which includes the title and abstract combined into one consistent column, the awards list, a flag if they are considered a winner, the total sum of money won from the awards, and some classifications for their award tier, as well as their general category. There were a few key things to note. That 2015 and 2016 were excluded from the category analysis as there was a huge gap in this data, and that 2020 was excluded from the award analysis as this competition was canceled due to COVID-19. 2024 was also excluded from the award analysis as there appears to be a data collection gap from the source data. So for some of the exploratory data analysis, a key element that I looked at after looking at the overall summaries of the data was the award tier distribution. The first observation is that the full distribution is extremely right-skewed and zero-heavy, as most projects do not receive any reward money, regardless of if they are classified as a winner. Among those who won award money, the top 50% of projects spans the entire range from $1,000 to the maximum of $252,000. Therefore, subsequent percentile breakdowns were used to clarify the tiers for the tier classification process. There's also some key structural findings. The next noticeable one is Tier 7, which is the 25,000 to 50,000 range, contains only two projects, as this is a natural dead zone that is hard to achieve through ISEF category awards and special awards. However, tiers 8 and 9 are large categories as they show these large award winners and combine stacking from special award organizations. 741 winners receive non-cash recognition only. So it shows that award occurrence and award magnitude are separate phenomena. And this overall represents ISEF's awarding process. Second exploratory data analysis process was used to compute the presence of AI and machine learning keywords, which were chosen to be artificial intelligence, computer vision, deep learning, machine learning, and neural network throughout the titles and abstracts of all projects. And this directly correlates to the first visualization, which is a line chart to show the rise of AI and machine learning keywords throughout these projects. This line chart answers the question by tracking these keywords. Machine learning rose from being present in 0.93% to 7.66% of all projects, showing an 8-fold increase, and deep learning showed a 67-fold increase. Overall, all of the keywords have increased in presence over time through three noticeable phases. As they began their presence, skyrocketed as they became accessible and popular, and settled as the novelty wore off, but they became a staple in ISEF projects. Deep learning is a specifically important keyword to note, as this was a topic and subset that grew and was discovered during this time. A line chart was chosen because it can track a trend over time where the year is a continuous and ordered x-axis variable. Connecting the data points via lines over the year shows the continuous process with the relation, and the line chart also allows for multiple series for each of the keywords to be overlaid without becoming hard to read. The chart uses some key visualization elements. It uses the vertical position of each data point on the y-axis and uses a common scale on the y-axis for the sum of the percentage. And the second crucial element for the visual perception is the use of color as a categorical distinguishing element for each of the keywords. There are also two slicers included for interactive elements for the user, where they can select a subset of the keywords and the years to be able to focus on certain trends and see those comparisons more clearly. The second set of exploratory data analysis is directly correlated to hypothesis 3, as this investigates how category growth predicts award win rate. This is based on the assumption that judges reward timely or culturally relevant science. This scatterplot answers that question by placing every ISEF category simultaneously in a two-dimensional space defined by exactly those two variables, where the x-axis is the percent point change for the category growth over the early years to the late years, and the y-axis is the win rate, which is the percent of projects in that category that receive an award. The null hypothesis is thus proven correct, as there is a lack of any discernible trend in this visualization. Otherwise, there would be a cluster of high growth, high success categories and a cluster of low success, low growth categories. The specific values reinforce this. The leftmost dot, which is the fastest shrinking category, has one of the highest win rates, and this actually correlates with the mathematic competition category. This can be due to larger categories being only able to reward a certain number of participants with the category awards, so the percentage of projects rewarded actually decreases. A scatterplot was chosen due to the two variables being plotted, as they are both continuous quantitative variables of the category change over time and the category win rate. The hypothesis asks about the relation of the two variables, so allowing the point to represent the combination of the two variables makes the relational trends and overall cause and effect more apparent. A scatterplot is also fairly standard fare for a correlation display. This chart uses the position along two common scales to show the relation between the x-axis and the y-axis. The axis actually crosses 0 at the left edge rather than in the center, which means that negative growth categories appear in the left portion of the chart and positive growth categories are to appear in the right. This is a useful layout because it separates the two groups and allows the reader to assess whether there is a visual difference between the portions of the data. The y-axis encodes win rate running from 15% to 50% at the top. Even though standard practice is to start at 0%, this does not start at 0 for a particular purpose. No ISEF category that runs in a competition year has a win rate of 0% due to the fact that they are guaranteed some form of winner in that category. And if this chart started at 0, it would artificially inflate the representation of the win rates. The second visual encoding is through color, which sets applied and computing categories as blue, separate from life, earth, and physical sciences, which are a red color. These are visually distinct colors and useful for categorical differentiation, and allows the user to look at the relation between growth and win rate through general scientific disciplines, especially as this project looks at advancements in physical and computing sciences. However, these disciplines occupy the chart with no discernible pattern. The data labels on each dot show the win rate, though this is not an essential element to have the specifics of due to the limited range displayed. A more useful metric would be the specific categories labeling the data points so that the user can more easily interpret each dot, which is a category, without referring to another table. Exploratory data analysis and is used to investigate hypothesis 2, which posits that certain ISEF categories receive systematically larger award dollar amounts regardless of how often they win, meaning that win frequency and prize magnitude are independent dimensions of competitive success. And this bar chart sets out to answer that question by sorting all 24 categories in competition years from highest to lowest average award value and encoding the win rate tier through bar color. The high win rate categories are light blue, while the medium win rate categories are dark blue. If hypothesis 2 were false, meaning that high win rates and high awards occurred together, the chart would show a clean color gradient from light blue at the top to dark blue at the bottom. However, the two colors alternate with no discernible pattern, which is the visual confirmation of independence. A sorted horizontal bar chart was chosen to compare category-level differences in award magnitude based on the category's overall award prize delivered. Individual category identification is easy with the bar chart, and the horizontal format allows the user to follow the way they naturally read. Sorting by award value and encoding win rate as color creates the most direct possible visual test of the hypothesis, allowing the reader to verify there is no trend. This chart uses the length along a common scale as a primary encoding, as this is an accurate, easy to understand element. The dollar formatted x-axis allows for more precise reading, while the general shape allows for trend analysis and general comparison. The x-axis starts at 0, since it's the majority of participants' experience, to not artificially inflate differences in winnings. The two key variables of the hypothesis, which are the award money and the win rate, are visually separated to make independence clear. The visual encoding is through color, as previously mentioned. And the current chart only shows the two tiers because there are no categories in the data set with a low win rate due to ISEF's reward structure. The discipline type slicer on the side allows the reader to filter the chart to either applied and computing sciences or life and earth and physical sciences in order to see the differences between the two domains, which could perform differently come changes in techniques. The user can also scroll over the chart to see the average award amount and other crucial information from the individual categories to allow for further analysis and interpretation. Overall, we were able to visually confirm hypothesis 1, showing that AI and machine learning topics have grown in presence in ISEF projects across the time span, and the shift is real, accelerating, and consistent. They are embedded in these projects. Hypothesis 2 was also confirmed that win rate and award money are independent, and that sponsor networks, not judges, drive prize magnitudes, as they have a lot more variability in their prize structure as opposed to the structure of categorical awards. Third, that category growth predicts win rate was in fact refuted, as judges reward rigor and other methodological and resource outcome related topics as opposed to the trend. Overall, ISEF judging rewards scientific depth and other elements regardless of whether a topic is trending, but its financial reward structure reflects sponsor priorities that are unevenly distributed, and students should take this into account when they pursue ISEF projects. In the future, this work can incorporate Google Trends integration to show how topics follow or lag public interest, country and university rankings to show educational equity and research topics, geographic and equity analysis, analyzing specific ISEF placements as opposed to the conflation of all special award and category awards, showing the topics with the most AI-powered tools, including research from more recent years, including latent topic modeling to uncover hidden themes and overall increased statistical rigor. The second